So we have parallel flow heat exchanger and it transfers 90 kilowatt using hot and cold fluid. So the heat transfer is 90 kilowatt and with mass flow rate of both hot and cold, that is 3 kilogram per second and 5 kilogram per second. And the corresponding specific heat of hot fluid is and cold fluid are 4.2 kilojoule per kilogram Kelvin and 3.8 kilojoule per kilogram. We have to just find the LMTD, logarithmic mean temperature difference. And also they have also given the inner temperature of both the hot fluid and cold fluid also given. So we need to find LMTD. So in order to find LMTD, we should find the outlet temperature of both hot fluid and cold fluid. So let's look how to solve this problem. So first, write the given condition. We have Q. The transfer rate is given the question, which is 90 kilowatt, and then the mass flow rate of both the hot fluid and cold fluid is also given, and the corresponding specific heat is also given, and inlet condition or the inlet temperature of both the hot fluid also. These are all mentioned in the question. We have to find the logarithmic mean temperature difference, that is theta m, which is theta 1 minus theta 2 by exponential log, or it could be ln or log, either way, ln theta 1 by theta 2. So before that, we need to find the outlet temperature of both the hot fluid and cold fluid. So we know the basic condition of heat exchanger is heat loss, heat transfer by hot fluid and cold fluid are same, and the heat loss by the cold fluid and heat gain by the cold fluid are both same. So you can use this equation, and they also given the values 90 kilowatt. That heat transfer value itself they have given the question. So first I'm applying for hot fluid case, and so I know the equation is mCp delta T. So mh mass flow rate is given. It's given in kilogram per second. So they're not we don't need any form of a conversion. If it's given in kilogram per hour, we have to convert it to kilogram per second, right? So it is given in kilogram per second, so we don't need to do any change, and the specificity also given. So by substituting the equation, one thing we have to keep in mind that when we're using equation, I have already said this in the previous previous video. When you're substituting using this equation, just check the unit of specificity. It should be in kilojoule per kilogram Kelvin, not in joule per kilogram Kelvin. Okay. When we're using the heat transfer rate separately for each fluid, not by equating, just using separate. Here we are using the hot fluid condition, right? We are separately using the heat transfer equation of hot fluid. So in that case, we have to what the unit of a specific heat must be 4 point. Okay. Then simple substitution, we get the outlet temperature of hot fluid as 142.86 degrees Celsius. Similarly, we can find the outlet temperature of cold fluid, which will be 25.26 degrees Celsius. So final step is just simple substitution. Just use our main equation theta m, where we already know theta 1 minus theta 2 by ln theta 1 by theta 2, where theta 1 is a temperature difference, inlet temperature difference between the hot fluid and cold fluid, and theta 2 is the outlet temperature difference between the hot fluid and cold fluid. So now we have all the value Th1, Tc1, Th2, Tc2. Only step is substitute the value and find the logarithm mean temperature difference. So this by substituting the equation, we will get the logarithm mean temperature of this parallel flow heat exchanger as 118 degrees Celsius. Okay, this is how we solve this problem.